Okay, so just for those people watching the video, the audio is my system audio because I didn't bring my microphone up. And we're going to talk about the start of exercise 5B. And a couple of things that you need to remember, and they are, first of all, that you need to recall your trigonometry rules, and in particular, right-angle trig. That's what you're going to be doing predominantly in this topic. It will come up, but it's going to be generalised. So you won't actually see where you have to decide and then appropriately apply trigonometry. You'll see most of the time that it appears naturally, and then you can apply it as part of the formula. But here's something really important. There's a couple of numbers that are going to come out of this lesson that you'll use again and again. I'm going to talk quickly about the globe. And again, if you're watching this, you might want to be picturing a globe on there. So here's our planet. It's a sphere, approximately. Not perfectly a sphere, so we have to make it go, but it's approximately a sphere. If we want to, what we're going to do in this topic is spend time talking about location on the globe and then distances between locations. So the couple of things I want to tell you first, which will be summarised up here as well in a moment. So firstly, you have two different measures to point out the location on the globe. So because this globe can be laid out in a two-dimensional shape, it can be two pieces of information, essentially. And they are, does anyone know what they're called? Longitude is one of them. Latitude is the other one. Does anyone have any way of remembering which one's which? So long. Yeah. Okay, cool. As long as you know, that's fine. I remember when I was going to school, longitude, I didn't know how to remember longitude, but I did remember latitude was like flatitude, so it was horizontal. That worked for me. So longitude and latitude. And so our latitude is a measure of how far above or below the equator you are. The equator, 0 latitude. It can go up to 90 degrees. Once you get to 90 degrees, you're at the North Pole, irrespective of where you're coming from longitude-wise. Once you get to negative 90, you're at the South Pole. Latitude goes between negative 90 and 90. And then we have the longitude. The longitude, first you have to determine whether you're in the east or western hemisphere. So this is done directionally as well. And it's done from the UK, which I've just gone past. There it is there. Done from the United Kingdom. That's a line of 0 degrees. And if you are in this half, which Australia is in, we have a positive value. So we are somewhere in the positive. This is the Eastern Hemisphere. And then the Western Hemisphere is to the west of the United Kingdom. And we have a negative value. Sometimes what they'll say negative 30 degrees latitude. But usually what you'll see is 30 degrees east or 30 degrees west. And so you have to work out from here. Remembering things, I know that we live on the east coast of Australia and that Perth is on the west coast, and I use that to remember which side I have to deal with. But you do it how you need to. Does anyone know why it starts here? Why 0 is in the United Kingdom? Greenwich, which is a place in London. Let me know why it starts in Greenwich. So just a historical thing, Greenwich has the of England, so there's the Greenwich Observatory in England, and that's not necessarily at the time the world leading observatory, but certainly the place that had the most influence, and so they have to decide where things go. So it's just a line in the sand. I said here this will be 0, and then we work from there. The result is that on the other side of the globe, over here, we have something called the international. Does anyone know what the international dateline is? Has anybody ever experienced flying over the international dateline? What happens? You what's it? You lose or you gain a day because we have time zones, and we'll talk about this in exercise 5C around the world. If you fly over the international dateline and you go back a day or you go forward a day, depending on which way you go. Now the international dateline is on that degrees line. I'm not sure what it is on that side. Maybe Alicia can have a look. It's down if you go sort of just east of New Zealand. It's sort of there. It is a line through the 180 degree mark, but what we didn't want is the international dateline to go through any countries, because then you'd have a country where if I'm here, it's Wednesday, and if I'm here, it's Tuesday. So they're trying to remove that problem. It zigzags in and out to avoid the Pacific Island nations predominantly. you'll notice it also goes in between, and you might not realise it, but Russia and Alaska are really close together. That's Russia, that's Alaska. That's which is the eastern tip of Russia, and Alaska is part of the United States of America. So close that they've actually talked about whether they could put a road tunnel underneath the ocean. It's only 60 miles or something between them. And another interesting fact that I learned a couple of years ago here is that there's an island, I can't remember what it's called, an island here that's in two parts. There's the smaller part of the island and the larger part of the island, and the international date line goes between them. There are families where one part of the family lives on this island, one part lives on that island, and there are so that's something interesting as well. Anyway, so that's what happens with the international date line. So there's some of the things you'll need to know about the globe. As it says on here, it has a radius of 6,371 kilometres approximately. So it's the nearest kilometre. Can anybody tell me the circumference of the Earth, if that's the radius? I'm just going to go ahead and say, you can all tell me the circumference of the Earth. You just need to work it out and calculate. 2 pi r is the circumference, really, yes?
Big number.
40,030. 40,030. Point. Go, give me 2. 17. Thanks. Okay. Thank you to this table who have given me an answer. The circumference of the Earth is 40,030.17. And that's actually really, really close to 40,000, which is, so you'll see often that 40,000 is quoted as the circumference of the Earth, and that's fine. And last lesson I talked about the guy called Eratosthenes who approximated. His approximation was about 40,000, so he was very close to the circumference of the Earth. That's what we use, but obviously the Earth isn't a perfect sphere. So around the equator is 40,030.17. Around other great circles, it's a little bit different, but we can use that value. That's a value that you can use. Now, I just mentioned the word great circles, and I'm going to finish this example in a second. A great circle is a circle that measures the entire circumference. You'll see this talked about in your textbook, and it's talked about a little bit later on here, so you can write it down. But a great circle is any circle that goes around the entire circumference. Whereas a small circle is a circle that is just a small part. It's a circle formed on the Earth. If you slice through the Earth, you create a circle, but it's not a whole circumference. You can get great circles. This pink one goes around the centre. This green one has dropped a little bit. It's a small circle. It's not a great circle. It turns out, I think this is addressed later on as well, if you want to find the shortest distance between, say, Brisbane and Perth, that will be the distance on the great circle that forms between Brisbane and Perth. If you think about it, obviously roads are a constraint, but if you could go in any direction, there are lots of ways to get from Brisbane to Perth. You can go from Brisbane and just travel north up over the North Mile and come back around to Perth in another direction that way. You can travel sort of up and back down. There's heaps of different ways you can do it. The shortest distance will not look like a straight line on here. And I find Australia, I've lost it, there it is there. It will not look like a straight line. The shortest distance will actually curve a little bit. But it will be the curve that's on the great circle. And so that's how we find it. Now, last lesson we talked about how we find an arc length, which is just a proportion of the circumference. If you want to find the shortest distance, you just have to find the angle between those two places. And that angle between those two places is just going to be based on their longitude and latitude. And then work out what proportion of 40,030 kilometres that is. So it's a fairly trivial circle, proportion, slightly trigonometry question. That's all you're dealing with. So, great circle, and I'll write this on here in case you want to copy this stuff down. And I would encourage you to do that at some point. But a great circle is a circumference, a full circumference, whereas this one here is called a small circle. use small circles sometimes as well. The radius of the Earth is 6,371. The circumference of the Earth is about 40,000 kilometres. If you wanted to find the radius of a small circle, well, you can find that by finding the radius of that small circle using trigonometry, as in this case. Now, this is a simple small circle. It's one that's just outlined around 20 degrees below, so at the latitude of 20 degrees south. But you can have small circles that are more around the globe rather than just flat small circles. But either way, we can use trigonometry to find how far away they are from a large or great circle. So in this case, if we're told it's 20 degrees below, and we know the hypotenuse is, because it doesn't matter where you go, from the centre of the Earth to the outside, we're saying is 6,371, which is 6,371, 20 degrees, and we can work out the radius of the small circle. Cos of 20 is equal to radius of the small circle over the hypotenuse, which is 6371. Can somebody tell me what 6371 times cos of 20 is? Looking for evidence that someone's got a calculator in their hand. One person, I've got one person. Andy? 5,986.78. Now, this is quite close to the original one, even though it's dropped 20 degrees. But remember that 20 degree drop, have a look in the globe. If I drop 20 degrees down, the circle doesn't actually get that much smaller. 50 degrees, it gets quite a bit smaller. 80 degrees, the circle is almost not there. But that first 20 degrees doesn't change it much. The radius of that works pretty well for me. And the circumference of that small will be equal to 2 times 5986.78. And Caleb, if you could throw that on your calculator with your answer you've already got. Stop and gambit. Oh yeah, okay, cool. Can you just throw that calculation in your calculator with the answer you've already got? You quoted one example, but you can get any longitudinal line as a great circle. So it's any circle around, fully around. So any of these. You can also get like these diagonal great circles. It just goes around the thickest part of the globe. Yeah?
But then how does measuring
well, it's not on a great circle like that, but if you want the shortest distance, it's always that distance on the great circle. So you see how my fingers are like that to create a small. If I spin it up, it creates even and per great circle. There will be one such great circle that's on, and that will be the shortest distance. But it's a bit tricky to calculate, so we won't actually get to that. If you've got two cities that are on different longitudes and latitudes, that's beyond the course. You will have to find distances between cities that have the same latitude or the same longitude, and then you'll be using the great circle that's provided there. But I'll be more specific. What do you get? Excellent, thank you. So that's a little bit smaller than what we had as well, but that's fine. We expected that. And here is a couple of examples before I let you loose on exercise. Oh, I see. I'm too. Oh, is there 2 parts? That's why I didn't make. There we go. There's a better diagram. There is a much better diagram. Look at that. Great circle. So we talked about great circles and small circles. About the shortest distance between 2 points being that on the great circle. I knew that was coming. And there's another diagram to show the distance between 2 points. The shortest distance will be that distance. Even though it doesn't really look like it, that will only be shorter if you actually drill through the earth. If you're going around the outside, it's shorter to go on the great circle. That's what the plane, yeah. And you know how when you're watching a flight and it's sort of curling, yeah, that's what a plane's doing. Following the great circle. So there's the blue ones are your lines of latitude, and the red ones are your meridians of longitude, or lines of longitude is fine. See these? The lines of longitude are always great circles. of latitude, only the equator is a great circle. The rest of them are small circles. And there's, yeah, where are we at? So there's some information on latitude there. You can have a read through that. North Pole has a latitude of 90, South Pole has a latitude of 90, but south. Longitude is measured east and west of the prime meridian, which is at Greenwich. And so you can see there's some good diagrams in here for you to follow. We've tried to be really careful about building this resource, not using your textbook diagrams, because then you can access these diagrams and your textbook diagrams. So you'll see mostly that's the case. So I think we're going to, there we go. Here's a diagram, and I would like to know if you can tell me what the location of A, B, C, and D are in terms of longitude and latitude. Okay, yeah, Google Maps. Not quite what we're after. But an Eastern Hemisphere, Western Hemisphere. So I've got negative 15 here, I've got negative 30, I've got negative 45. So C has a longitude of negative 45 or 45 degrees west. Equally as good. You don't have to do negatives, you can just make sure you annotate that it's in the Western Hemisphere. Also, in terms of that's all on there. Okay, so D's on the equator. That's 30. That's 60. Yeah. Oh, I see. No, here we go. The dotted one's there. So 15, 30, 45, 60, 75, 90. So the dotted one's there. So C is 45 above. So it's 45 degrees north, and then it's negative 45 degrees or 45 degrees west. So if I just note this on here, 45 degrees north, 5 degrees west. Now you have to be a little bit careful here. It won't really matter, but typically we'll do the north-south first and then the east-west second. That's what you're, which goes a little bit against what you'd normally do on a linear function, because you'd normally do your x-axis first and then your y-axis. So it just reverses from that. This is the equator, so that's 0, which means that this is 15, this is 30, and this is 45. I hope you can see D. I'll just jump to D because it's the next one on that list. Is 30 degrees north and 0 degrees east to west. Doesn't really matter which one I put. B, oh, that's C, isn't it? Done them in a weird order. Let's move C down to here. E is here, which is 15 degrees north and 30 degrees east. 15 degrees north, 30 degrees east, and then A is 45 degrees north and 30 degrees east. And you can also find longitude and latitude on Google Maps as well if you need to. So that's exercise 5B, and you should be able to do it to question 6.